PhD. So at 5 will be 5 sixths, 6 sevenths, 7 eighths, 8 ninths, and so on. We will try to get closer and closer and closer to that, but never do. Yeah? So if a sequence does seem to reach a point like this, that's called the limit of the sequence. Okay? This is not the, it's like a similar concept to that of like a limit of a continuous function. But it's different. It's not like that definition, because there you're taking the limit from the left and from the right, getting close to x values among infinitely many values close to it, right? Here there is no such thing. There is 1, then there is 2, then there is 3, then there is 4, and you're just taking the limit as n goes to infinity. Okay? So in this case, for example, we say if I have a sequence an has limit L at infinity if
Smart.
the difference between a and L can be made arbitrary. I mean, the difference can be made arbitrarily small. By taking n bigger than some capital N. That's a very loose definition. But I mean, I can give you the proper definition, but if you want to see it. It's like saying if I want to be within a third of 1, I can choose to take points from 2. If I want to be within 0.1 of 1, I choose from 10 onwards. The points will be within that distance of 1. So because I can get arbitrarily close to that point is the limit. So everyone sign?
Oh.
And then pass it back. Okay?
Hmm?
So this
Double
is
one.
like calculus, except we're thinking of limits at infinity. Limit as something x goes to infinity. This stuff is so this next half of the course is slightly more challenging than the integration bit. But this is not. This is sequences. This is literally baby stuff. It's like you have a list of numbers, a bunch of numbers. They seem to be going somewhere. Do they just go off to infinity? Or are they just moving about in space left and right? That's all. Right? If a bunch of numbers are going, you have a bunch of numbers. Oh, they look, they're getting closer and closer to 1. 1 is the limit. Right? That's all. If you have numbers like this, root 1, root 2, root 3, root 2, doesn't look like they're ever going to stop. Their limit is infinity. Or something like this. What do you think the limit is here? Looks like 2/3 minus 5 ninths, 8 27ths, minus 11 81. And then the next one, which is plus 14 over 300. What is it? What's 81 threes? 243. That's much smaller, right? And the next one is going to be over 3 to the 6, which is 729 or something, right? So you keep going with the denominators get much, much, much bigger than the numerator. And so what happens to the ratio fraction? It approaches 0. It's like these numbers are dancing around 0. Because you have, if I try to draw this sequence here, right? If I try to draw its graph,
But it approaches from both sides.
it approaches from both sides. So the first one is 2/3, right? But the second one is -5/9. Then the third one is here, then the fourth one is here, then the fifth one is here, then the sixth one is here, then the seventh one is here, 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 here. They approach the line 0, but by being positive and negative alternately. So the limit is 0. So the limit is in this line. And you could draw that same thing here. You could have said this is the first term, the second term's here, the third term's here, fourth term's here, fifth term's here, sixth term's here, seventh, eighth. So it goes like this, then this, then this, then this, then this, then this. And eventually it looks like it's going towards 0. But from both sides, alternately positive and negative. It doesn't matter. The limit is 0. Luckily, if you have a sequence, an, right, and somewhere to infinity, let's say 1 to infinity, that is given by a formula f of n, some function f of n, then limit as n goes to infinity of the sequence an, not the sequence of an itself, is the limit as n goes to infinity of f of n, the function f of n, in the calculus sense. So this limit is in the calculus sense that we've used before, meaning you continuously now think of n not as an integer, but like 10 and 10.1, 2, 3, like continuously changing and going to infinity. If you let n go to infinity for this f of n, you take that limit, that will be the limit of the sequence. So you don't have to worry about what might happen.
So I just think of it as a graph, right?
Yeah, you just think of it as a graph. And you calculate its limits like you would calculate limits at infinity as before. So for example, if you're trying to calculate a limit and it's like an infinity over infinity situation, you can use L'Hopital. For example, here, this sequence over here, if I need to find the limit as n goes to infinity of -1 to the n, 2 plus 3n over 3 to the n plus 1, like this, that looks like infinity over infinity. So I'm going to change it to a function f of n, which has exactly this formula, right? But now n you can think of as a real number, not just an integer, not just 1, 2, 3, 4, 5, but continuous band of integers, real numbers. And then you can apply L'Hopital rule. For continuous differentiable functions, you can apply L'Hopital rule. You can't apply L'Hopital rule in step 1, 2, 3, 4, 5. But if it's a continuous domain, it applies. So what do you get if you apply it? Actually, I should be more careful. Let's just forget about the -1. So now what do you get if you apply L'Hopital rule? L'Hopital rule?
N plus
3
1,
over
P
n
plus
plus 1 times 3 is
That's
3. Just 3 over
n plus 1 n plus 1 is
3 to the n plus 1 log 3. That will be the derivative of the denominator. And maybe the plus 1 will cancel with this 3 or something. But either way, it's a number and the 3 to the n is going to infinity, so that's 0. Right? So instead of showing that an here goes to 0, we showed that the limit of absolute value of an is 0. Right? We forgot about the plus minus bit. We just took the positive part of the sequence and showed that goes to 0. Yeah? Okay, let's see how we can deduce from that the sequence itself. So there's a couple of things to do here. Firstly, when you think of these sequences as functions given by some formula, the usual rules we had from calculus of what, for example, the squeeze theorem is still true. Like if I have sequences an, which is always less than bn, which is always less than cn, they don't need to be positive or anything. The sequence is an less than bn less than cn, right? And if the limit of an as n goes to infinity is the same as the limit of cn, then the limit of bn exists and equals that limit. Right, so you have an is less than bn is less than cn. This goes to some limit, and this goes to that same limit. Then we're saying this one exists and equals L. If it's squeezed between two sequences, and those two sequences have that same limit, then the sequence squeezed in the middle must have the same limit. Just like the old squeeze theorem, you know, and remember, right? So like the picture that goes with this is what we have. Let me make this much finer. So I have one sequence an and another sequence cn, and I have a third sequence bn that's somehow stuck between these two. Well, if an achieves a limit at infinity that is the same as the limit that cn achieves at infinity, then bn, being stuck between those two, will achieve the same limit. Okay? So it's very easy, right? There's nothing, no one would doubt that, hopefully. So then, what that tells you is that if absolute value of an goes to 0, then an must itself also go to 0. If the limit of absolute values of an is 0, then the limit of an must also be 0. Can anyone show me how this follows from the squeeze theorem?
Minus a plus a go to 0.
Minus an, as in what minus an? Minus just an? I don't know where an approaches. I only know that absolute value of an approaches 0. So I have to use that. But you're right, that is the correct train of thought. So how should we write?
The left hand limit and the right hand approaches 0.
What is the left hand and what is the right hand?
an minus 1.
Okay, maybe if it was like 9:30, you would get it, right? But the proof of this is minus absolute value an is always less than an is always less than absolute value, right? Because this is the positive bit of an. If an is positive, then it's equal. If If n is negative, then it's equal to this. But either way, it's between these two. And if this limit exists and is 0, then this limit exists and is minus 0, which is also 0. Right? So then this must also exist and be 0. Yeah? Yes? So now what do we conclude from that? From this we can conclude, for example, that this sequence, the alternating sequence, also has limit 0. Because the one without the signs, the absolute one, that had limit 0. And if you're going to 0, it doesn't matter if you're going from the left or the right or both, you're going to 0. That's it. Okay. So basically, we did the graph, the line visualization, the limits, the limit of the sequence, the definition of limits, and squeeze theorem. Wow, awesome. So let me give you some examples of divergent sequences. Because sequences may diverge in different ways. And then, how about someone from the back? Yeah. Sure. Yeah, if the nth term is given as the value of a function at n. If you can write a formula for it, that's yeah, because those are the only ones we're writing. But generally you could have a sequence like this, which doesn't have a formula.
Anything that has a formula is a function.
Yeah, that formula you write down is the function. If you know the formula, for example, if it's defined by recursion, you don't know the formula. So what are you going to evaluate? Take the limit. If you don't know the formula, then it's a bit difficult.
Because earlier you said that the limit of the sequence is not the same as the calculus limit.
Yeah, conceptually it's a different thing. Because in calculus you take h goes to 0 from the left and the right, and it's a continuous going to 0. Right? Here, or when you go to infinity, you continuously go to infinity.
Yeah.
But here you're going in discrete steps, 1, 2. That's the difference. That's what I mean.
We can still equate them.
And you can still equate them if you have a formula. Then you just treat the formula as if it was a continuous function and take its limit. And by continuous, I don't mean continuity. I mean
Yeah.
without gaps. A function defined as an interval without gaps. Okay, so if you're just arriving, that's what the sequence is. It's just a list of numbers. There's nothing to it. It's just a list of numbers. If you give that list of numbers with a formula, like where the first one is that formula evaluated at 1, the second one is that formula evaluated at 2, and you get a formula for your sequence, right? And you could have a sequence of anything, and these numbers in the sequence, if they seem to be approaching some specific value, finite value, that's called the limit of that sequence. If they don't seem to be approaching a specific value, then that sequence doesn't have a limit. It's called divergent. And that's it. And they're squeezed. If a sequence is squeezed in between two different sequences, and the outer two sequences have the same limit, then the squeezed one must have the same limit. Yeah? Any questions about this? Okay, so back, tell me what this sequence is. Something like this. So, there's someone who is asleep. Can someone who is asleep tell me? Well, I guess the people who are asleep can hear me. Yes? Just someone from the back. Can you tell me what the first term is here? Not you.
Yeah.
You can't read this? Seriously? I don't believe you. How about now? Hmm? 3 by 10. Yes. And the second term?
One by 25. 1 by 25.
4 over 100.
Isn't it like 4 by
No,
100?
someone said
Yes.
One by 25.
Hmm?
4 over 100. I see.
It's not what I'm saying.
And then just 5 by 1000. And then 6 by 10,000.
Sure, please.
So for instance, what's the limit of this sequence? Is
أول واحد تسوي
the
N
terms are
by
getting
1.
very small.
ثاني N.
They'll go to 0. Yeah? So, this was stupid on my part to write this function because 2 to minus n is just a 2 to the n in the denominator, which is just a 10 to the n. So it just goes 10, 100,000. So very much. Okay. Let's see a couple of examples of divergent sequences. So, for example, if I have the sequence cosine n pi, right? How does this sequence begin?
No, yeah. No, cosine of
Minus 1. And then? Cosine of 2 pi? 1. And then cosine of 3 pi? Minus 1. And are you doing that on your calculator?
Yeah, I don't know the.
Okay. Okay, cosine of 4 pi? That's going to be 1 again, right? But don't make the mistake of, like, people do this in Calc 1, right? Your calculator is not in
What is this?
radians, and then you
Yeah,
calculate
yes.
cosine of 2 pi and it comes out like 0.1 something. Yeah, so anyway, this sequence is alternating between -1 and 1, -1 and 1, -1 and 1. So what is its limit? It doesn't exist. So we can say limit of the sequence cosine n pi n goes to infinity does not exist. Because it doesn't get close to any one particular value, it keeps oscillating between -1 and 1 and -1 and 1 and -1 and 1. It never really settles on the value. If you want to graph this, over the integers 1, 2, 3, 4, 5, 6, 7, you'd get, minus 1 and 1, then 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 minus 1 and 1. The sequence never settles on 1. Right, right? Similarly, the sequence we had earlier, root n like this, its graph looks like a parabola, but it's still a parabola. It goes to infinity, right? So again, limit as n goes to infinity of root n.
Infinity.
It's infinity. It doesn't exist. What is infinity? Depending on how you. Either way, it's called divergent, right? So this sequence and this sequence, they're called divergent. Which is to mean the opposite of convergent. And convergent is if you have a limit that's a number. Okay? Okay. Did the people sign, right? Everyone signed? If you didn't sign, come back. Here's at the end.
I think I'm seeing
Okay. Yeah, this means so if you have a formula, it's easy, right? If you just take something like n over root of 10 plus n squared. This sequence, does it have a limit? Yes. And what is it? It's 1. What about if it was 3 over root of 10 plus n squared? Then it would be 0. And what if it was 3n squared, or 3n, just n, over root of 10 plus n? It would be infinity, right? So these two are convergent. This one is divergent, right? So you just calculate limits of sequences just like you would calculate them in calculus. Now, how is he calculating it so hard, so fast?
So like you take that n out of the root and then you can just check the power of n in the numerator.
You check the difference in powers. Find the highest power in the denominator, highest power in the numerator. If they happen to be the same, like here in the denominator the highest power is a 1, because it's a square in a root, and here the highest power is 1, then you just compare their coefficients and that's the answer. Take the ratio of their coefficients. If you want a more formal proof, what you do is you divide by n, both, you get 1 there, and in here you'll have 10 over n squared plus 1. The 10 over n squared goes to 0, and you get 1 over root 1. Right? You remember this? When you had these polynomial over polynomial, you divide by the biggest power of the numerator and the denominator to find the limit at infinity. All limits at infinity are, most limits at infinity are like this. So you just do this. And since sequences, we will always be taking limits at infinity. It's a very useful trick. Okay, so I think you got this. So Another example I have here is if I have the sequence log n over n. Right? So this sequence starts log of 1, which is 0 over 1. Log 2. Log 3 over 3. Log 2 over 2, right? Log 4 over 4, and so on. Log n over n. Does it converge? Does it diverge? Does it have a limit? So you should treat it like it was a function. You should think, does log x over x, as x goes to plus infinity, have a limit? Right?
Zero.
And it does? It's 0 y.
It is zero.
By L'Hopital's rule, because it's an infinity over infinity thing, so you take the derivative of the numerator, derivative of the denominator, and that limit is 0. So by the L'Hopital's rule, it has limit 0. So this sequence does approach 0. It has a limit, it does approach 0, it's convergent. Okay? So we'll use the same tricks of calculating limits from before, apply them to sequence. Now, sometimes you have to calculate limits of sequences that are recursively defined. You can assume that the limit exists. That's a bit more complicated, we'll get to it later. So this is the next result here, which is this looks like the result we had before, but it's that f of a sequence will converge to f of the limit of that sequence if the function f is continuous. Okay. Right? So, in other words, the limit as n goes to infinity of f of a n is f of the limit of a n's themselves. So you can take a limit inside a continuous function. So for example, this sequence is continuous, right? This sequence has a limit. So you have limit of n over root 10 plus n squared as n goes to infinity is 1. By whatever, by L'Hopital, some other rule. Sine is continuous everywhere. So, what do we get? That sine, the sequence sine of n over root of 10 plus n squared approaches sine 1. That you can do, take the limit of the inner function if the outer function is continuous. Does that make sense? This is very often you have something like, okay, these sequences we can deal with, right? But what if we had a sequence where there was a sequence inside a sign or on top of an exponential or some other crazy arctan or something, right? So if I have something like e to some sequence. So I don't know how to deal with that, right? Are you all thinking about the first midterm and thinking this stuff we'll learn about it a month from now? 2 months from now? So I don't like this. Okay. Right? Do you understand? Like sequences like this by themselves, yeah, we can do. We can take a limit. What about sequences that are inside other functions? Like you have arctan of some sequence an, and now it's a new sequence, and to calculate its limit, we're saying you just take the limit inside, compute the limit there, and then apply it. It will be the same as long as this function is continuous at the end, at the limit. Okay? It doesn't matter, I'll say it 10 times and then when we have to use it, you won't remember it. Right? I know. So it's really.
Of the
Yeah.
sequence
But
itself.
do we have to
Okay, then just
substitute
substitute
the
inside.
exponent?
That's it.
So the functions we use, sine, cos, trig functions, log, exponentials, inverse trigs, polynomials, rationals, they are all continuous on their domain. This is from one of the results from calculus, right? So for those functions you can just state that this function is continuous on its domain. So I can just use it. Exponential, for example, or arctan or sine are continuous everywhere. They're differentiable everywhere. They have nice tangents everywhere. So these are really nice functions. If you had something like tan instead, or like log, or like root x, then you have to worry about their domain. You need to be on its domain. So for example, here you can't take x to be plus or minus 90. Here you can't have x be less or equal to 0. And here you can't have x be less than 0. For continuity, you can have it be 0. Even at 0 this is continuous, but not for negative number. You can't define it. Right? Yeah. So that's good. So if you have a continuous function, you can take the limit inside. That's the idea. Let's look at a specific sequence now. Just for a minute, because this will become important in series. Series are not just sequences, but where you're adding terms of a sequence. You add the first to the second to the third. And you add bigger and bigger pieces of the sequence, and that's, when you add it up to infinity, that's the series.
Do you have to memorize like the formula for geometric and arithmetic series, or do you just give it to you? Because they're very big formulas. They're complicated.
On your, when you have the test for this, you will wish that you have a geometric or arithmetic series in front of you, because the other ones that you will most likely encounter, things with logs inside, arctans and exponentials and things like this, series for which you have to use like some tests. I mean, I don't mean to scare you, but you will automatically remember the formula for the geometric and the arithmetic series. Those are the only ones where you can calculate stuff. and it'll be a very small part of your calculus. But for the others, I've already made a sheet of all the possible tests you need and all the techniques for like the series. So once we get to that, hopefully that will not be too bad. Let's just look at one basic sequence rather. First, let's look at just r to the power n, where n say goes from 1 to infinity, right? For what r does it converge? Yeah. So strictly less than 1 and strictly bigger than 0?
The index is 0.
So when r is 0, we have the sequence 0 to the 1, 0 squared, 0 cubed. We have the 0 sequence, which does have a limit. It goes to 0. When r is, let's try 1. Okay. So we get 1 squared, 1 cubed. That goes to 1 because it's 1, 1, 1, 1, 1. The whole sequence is 1. Goes to 1. Let's try minus 1.
But isn't it that 1 raised to infinity is
We're not doing 1 raised to infinity. We're just looking at the terms until then and seeing if they converge. So we generally avoid doing things like that. So what about if it's minus 1? Minus 1 to the 1, minus 1 squared, minus 1 cubed. Right, I'm talking about the sequence r to the n, where r is some number. When r is minus 1, you have minus 1 to the 1, minus 1 squared, minus 1 cubed, minus 1 to the 4th, and that's minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, right? And that limit doesn't exist. How about, now let's take r to be something like, huh?
A fraction?
Like 4 over 3?
Yeah, like 1 over 2.
1 over 2. Yeah, let's write it like, say like 11 over 10, 1.1. As opposed to like 0.9. Yeah? So what do you think happens in this case? If it's more than 1,
it is infinity.
you have 1.1, then what, can you guys see this? 1.21, that's not too bad, but it grows, right? So it's like 1.1 cubed, 1.1 to the 4th, and that actually goes to infinity. When you keep applying this, again, it gets slightly bigger, slightly. Each time it gets bigger by 10%, but 10% interest compounded infinitely. Go to infinity, right? What about this? Starts 0.9, it's squared, 0.81, it's squared, something like this. I mean, it's cubed, and then dot dot dot, keep going, right? It gets smaller. Eventually goes to 0, right? So, what's the rule?
Between 0 and 1. Cannot be more than 1.
R cannot be more than 1. It also, yeah?
Cannot be less than 1.
Huh? No, that's okay. So, for example, let's take R minus 0.9. Yeah. So minus 0.9 plus 0.81 minus 0.729. They are alternating, but they are getting really small. So this would still converge to 0. Right? So Rashid, can you tell me? What R makes it converge and what R makes it diverge?
I would say it diverges the DNE, not DNE, I mean the infinity.
Both
Yeah,
of these are divergent.
yeah. Both of them.
So when does it converge exactly?
Between 0 and 1.
But this one also converges. It's not between 0 and 1.
Is it just because it's negative? Or? So negative 0.9? That's it.
What?
I mean, that's it. 0.9 and negative 0.9.
No.
It's
I don't
not?
know what you're saying. So can you say clearly when does it converge?
I'm saying it's diverges when it's DNE or infinity. And what's it called?
So you're saying it's divergent when it's divergent.
Yeah.
For what R is it divergent? Yes.
Ah,
Can you
that's
tell me
what-
from the back?
When does something converge or diverge?
Good. So you were sleeping in the first half of this lecture. You just told me. When it has a limit, that's not infinity. Something converges if it has a limit.
Diverges?
If it doesn't have a limit or its limit is infinity. I thought you were answering the question. Can someone answer the question? Yeah, you.
It's converging from -1 to 1.
And what about the endpoints of that? So -1 to 1.
R is less than 1. R is less, I think,
Less than equal to.
Yeah. And then this -1 is less than 1.
Not equal.
Yeah.
Yeah, it's this interval. So it's -1 to 1 like this. If R is in that interval, it converges. Okay? Is it time?
Right.
What time?
It's not.